We call this 1D wave equation. We found it to study sound waves, waves in a string, and later waves in solids. But as you can imagine, if you want to work in a 3D environment, you should add also the y square and the z square. What about the solution? For 1D.
1D.
Okay. Okay.
Omega t minus
wave vector.
Good. Thank you. Now, it's a plane harmonic wave. Plane because it's not decaying with distance, but we know, because we did it, that for spherical waves, okay, should be something like that. In 3D, wave vector should be a vector pointing somewhere, and this has to be a scalar product. And that's the solution of the homogeneous equation, right? Just as a recap. So, our differential operator is this one, with the Laplacian to take care about the 3D world. And we solved it. Good. Now that's the new term. Okay, let's, if I don't connect it, what's going to happen? Okay, while I'm setting this up, you can read it. We can manipulate that equation staying in some place or taking a given time. And what we're looking for should have a radial symmetry. Okay, because the problem is symmetric, spherically symmetric. So we have to care about the distance from the origin, where the source is, and time. Now, we know that when this is 0, the solution has to be like that. But wait a second. You remember Monsieur d'Alembert? D'Alembert was saying, you're smart, you're taking a very nice solution, sines and cosines, and thanks to Monsieur Fourier. And it is a complete set. But in general terms, a solution of the wave equation in 1D, it's this, Monsieur d'Alembert. Okay. Now, just to take care about the distance of the origin, and since we're living in a spherical world, so we should have a decay like a spherical wave, the solution has to be like that. Distance divided time, if you take the time out, x over v, and that's it. So that has to be the message that is going to be spread around the source, because we're living in a problem, in a world where everything is symmetrical around the origin. Now, what about t equals 0? Okay, if you take t equals 0, and so that is 1, what we have here, it's not a dynamic problem, but a static problem. And it's called the Poisson equation problem. And we know how to solve it. Actually, you did it, for example, to study the electric field radiated by a charge. And that's the solution. And if you want to take care about the, how to say, normalization in a sphere, a 4 pi is coming here. And the c square is coming here because it's here. So for this problem, the general solution is like that. A delta is starting, a delta is going to be propagated. This is a normalization factor, And this has to take care about the conservation of energy because it's a spherical wave, radiating like that. So nothing is new here, because actually putting a delta in time and in space and preserving the radial symmetry, we got the solution that we were waiting for. So that if you have a center that is spreading waves in a symmetric fashion, okay, it has to be a spherical wave. The energy is going to be spread on something that has an area 4 pi over times the square of the distance. That's why, if that is going to be the energy and the energy has to be preserved, amplitude has to be 1 over r. It's a spherical wave. Good. If the message is a delta will leave. So if I'm clapping my hands here, okay, you're going to hear the clapping of the hands. Let's think about one thing. The system now is homogeneous and infinite. So we have no reverberations. When you clap your hands, you have a reverberation here because we are in a closed domain. Okay? Here the system is infinite, homogeneous. We have just one velocity. Could be a p wave. Could be an s wave. No, it can't be in this problem an s wave, because no s waves are generated by pure, perfect, and a peaceful explosion. So it could be a wave velocity, like p waves, okay? So 4 pi is coming from the integral of the sphere. Psi square, c square is there because we have it here. And the algebra needed here is just to solve the Poisson equation. And we know how to do that thanks to the mathematicians. If it is 0, we're going back to this. Okay, that's the general solution. Everything is fine here. And with a rapidly varying function, it's a delta. It's an impulse, because the delta is here. Please remember that for the information to reach us at a given point, far from the origin, we need to wait the time. It's called retarded time. That's physics. So to get the message, we need to wait the signal to reach us. Distance over velocity. So we have a source term, and the source term is going to be propagated here with a perfectly symmetric fashion. Is it the end of the lecture for today? No. Because actually we have to take care that we need to answer to another question, a direction here. So if we are pushing, yes?
Okay, one confusion regarding the solution of the Poisson solution. Delta u is equal to delta function by c square. And after integration...
This c square is coming from here.
Yeah, it's okay. After integration, I think it would be u is equal to 1 by 4 pi c square only. Because integration of delta function over dx is 1, yeah?
Mm-hmm.
So that's why dx...
I'm not sure if I'm catching your point. By the way, if you look... Let's see if I have it here. Here I was leaving something from the Helmholtz Theorem. Okay, it's here. Okay, if you're brave enough, you can use Aki and Richards. The chapter is chapter number 4. What we did in the previous lecture had been using chapter number 2 and 3, and trust me, they contain what we discussed with much more details. So, as I told you, I'm grabbing steps of this book here and I'm trying to make a sort of a synthesis here. But if you give a look to this one, okay, I'm catching it. And I think this solution with all the steps is here. So since you're a brave person, you can use this textbook and go to box 4.1. And I think, as far as I remember, that here you have all the details with the integration, and there you go. That's the solution of what we are looking for. Any mistake on my slide, it's my fault. This textbook has some typos, there are corrections if you Google it, but not in this box here. So the answer to your question is here. I'm a lazy person, you know, okay?
It's not accurate.
Okay, but thank you. Now, what can we do? Well, actually, since the differential operator that we are considering is linear, we can use its linearity to get some additional properties that are quite intuitive. The first one, let's imagine now to move the source into another place and to switch it on at another time. Okay, solution is easy. What is necessary here is just to measure the distances from the place of the source and to start the clock from the initial impulse. So that's intuitive. Second, since it is linear, if instead of playing a delta, you take a singer that is singing something beautiful, so if you're considering an f of t instead of a delta of t, f of t is the function that is going to be propagated. Okay? And this property, for brave persons, the proof is there, is just related to linearity. A wake-up question. Can you imagine some property of a medium that can change the f? So I'm telling you, if delta is leaving, delta is going to be transmitted into the medium. Can you imagine some property of a medium that can change the delta? For example, spread it.
The medium is not homogeneous.
Okay, that's one possibility, because you have reflections, refractions, and so it's going to have different phases. But there is another property that you can imagine. Dispersion. Please do remember the dispersion we discussed in the wave physics course. For example, not exactly the waveguide dispersion that we studied in wave physics for lava and Rayleigh waves, but for example, the dispersion of light into the air or into water, you're going to spread, and you have rainbows. So dispersion is making different frequencies to travel with different velocities. And this means that a delta that contains all the frequency is going to be spread. Okay? So dispersion is one factor. And maybe, I hope, in one of the final lectures of this course, we will find a strange property that will give dispersion with homogeneity. And that will be anelasticity. But that's for the anelasticity lecture. Okay. Final property that is again connected to the linearity of the problem. Now let's imagine that the source is not a point, but it's something. Well, okay, we can sum, you can imagine to divide the source into different pieces and to sum them so that if you take the integral of the radiation, you will get the integral of the radiation. Now what is funny is that we're solving here an elastic problem, but all these formulas here are the same for optics. Just the same. Actually, not Messier because he was German, but Fraunhofer, I'm not able to speak German, so, okay? Fraunhofer, Huygens, and other people was using the same formulas for light. And C could be the speed of light. Okay. That's the end of a nice part of a lecture. Because what we have to do now is to solve a delta in direction. And that's a problem. And to do that, we will use a good old friend. Maybe it's a new friend for you, I don't think so, but it should be an old friend for you. because we used it to solve the wave equation for solids. This is a general theorem very used in classical mechanics. It's called Helmholtz Theorem. Actually, it's not that easy. I'm going to use it in a very simple way. But if you give a look, for example, to that link, or if you Google Helmholtz Theorem, you will see that it is studied by mathematicians. For example, that's not the link, but it's a document very similar to this one. And you can find pages of analytic mechanics, for example. We are going to use it in a very simple fashion, as we did it for the wave equation in the wave physics course. Helmholtz theorem is saying, okay, if you have a vector field, you can always write it in terms of a gradient of a scalar function plus a curl of a vector function. And we used it for P waves and S waves. We are going to use it today not for the waves, but for the source. Because what we did up to now, we had been solving a symmetric problem, okay, but now we have a direction. This is the difficulty. And the idea is to break the problem that we have to solve with direction in pieces that can be solved with the symmetric problem. So to reduce the direction problem to the other one. And the way to do it is called Lamé theorem and is using Helmholtz theorem. That's the theorem. Actually, if you want to be more sophisticated, you should put some conditions on the vector field and of the potentials. That's why I was adding the link. For example, in some versions of the Helmholtz theorem, someone is adding a condition of a divergence of psi. That should be 0. I'm not adding those details. Why? Because the vector fields that we have to study are very simple. It's a displacement field. And it's polite. Additional condition should be, for example, that the potentials and the vector field are going to 0 at infinite distances. Okay? That's a politeness request. And in our case, it is. Let me just tell you that to express with some, how to say, mathematical politeness, additional conditions on U, phi and psi are related to uniqueness problem. Because Helmholtz theorem is saying to you, okay, if you take a vector field, you can break it into two parts. Question, is it a unique solution? Do we have a unique solution? Answer is yes. So to have the certainty of having a unique solution, it's fine. A way to prove it, if you remember, is, okay, because now, if you want to solve the Helmholtz theorem, you can say, thank you, Mr. Helmholtz, but how to find the two potentials? And Helmholtz is saying to you, okay, look, take the Poisson equation with the inhomogeneous term as U, okay? Now you're looking for a W function. Well, this solution can be solved thanks to Monsieur Poisson, and that's the solution. We have been using it. Okay, so you could say, and so what? Well, if U is going to 0 at infinite, the solution is unique. And once you find it, okay, now if you use this property, that the Laplacian can be written as the gradient of a divergence minus the curl of, okay, if you take this solution and you take the divergence and minus the curl, you get the potentials. And this is giving us a hint. So the game is, I give to you vector field U. Find the potentials. If you remember, we did it with P and S waves. Okay, thanks to Poisson, what we have to do is to write the Poisson equation related to U, find W, take the divergence and the curl, and then we have the potentials. okay? Because if you take this, if you take the divergence of this and you apply it here, and you write this with these ones, you will see that the potentials that you are looking for are the divergence and the curl of W. So it was a good old friend. Do you remember? Okay. Now it's time. This is what we have to solve. Bad news. Very bad news. Because Newton, good. Lambda in mu, okay, we're homogeneous, isotropic, infinite medium. So lambda and mu are given, and they are enough. And we solved this solution when f was 0. If you go back to the wave physics course, you can find this equation. And then I told you, okay, who cares about f? Let's forget about gravity. You remember? I hope so. And we solved it. And these were p waves, and these are s waves. And we found two wave equations. And if you remember what we called alpha and beta, okay. P and S waves. Two wave equations with two velocities. Game over. Now the game is starting again because now we have F. Pay attention, now F is not gravity, it's a force. It's a force that is pushing our system. How to solve that problem? Okay, let's try to break F using Helmholtz Theorem. We have used Helmholtz Theorem to find this. Now let's use it again to break F into a scalar and a vector with a scalar and vector potential. Okay, yeah, I know. This is just the synthesis of Archian Richards. Now, I'm not going to ask you all the details of this poem, okay? Just the logic. The logic is, we have this problem here, and F is a delta in space, time, and direction. So we cannot use the previous spherically symmetric problem. But we are trying to break this problem into something that is similar to that one. Okay? Now, if now we take our body, maybe we apply some boundary conditions, but since it is infinite, we do not need them. It's homogeneous, it's isotropic, and we define initial conditions. Okay, now we can take the F term and we can break it, thanks to the Helmholtz theorem, with two pieces. Okay, so now these two potentials, scalar and vector, are representing the source. Okay? Okay, and these are the properties that we have to work for, and now we have this. Wait a second. What is the idea? To take this equation, that is complicated, use Helmholtz theorem for displacement and the body force, and what we're getting here is this. U can be written as the gradient of a scalar product plus the curl of a vector product, and now the two potentials that are defining U have to satisfy these two equations. So the logic is, let's start with that, let's apply Helmholtz theorem, and let's break it into different small pieces. The problem now is reduced from this one to these two. Do you recognize something in the two problems?
Yeah.
Well, actually, if you get out these two terms,
It's exactly like
P waves and S waves, and we solved it. So actually, thanks to Helmholtz and thanks to Lamé theorem, now the problem that we have to solve with this F can be reduced with these two. What is the problem in these two? Well, this and this. But at least we separated the initial problem into two smaller problems. Okay? It's not the end, because now we have to find the two potentials that are satisfying these two equations, that are wave equations, 1 and 2, inhomogeneous, of course. Good. Let's take an example, just to show to you how this process can be solved in one case. And the person that was solving this was George Green. Yeah, same of Green's function, with the help of Stokes, as far as I remember. Okay, now let's imagine that F is a specific force. For example, it's a delta in space, so it's a point in the origin. It has some time function. You have seen that for linear problems, the time function is not important. It could be a delta, it could be a singular. And this one, now, is pointing in one direction. So let's imagine this is 1, 2, 3. Now the force is in this direction. Okay? What are we waiting for? Can you imagine something? Okay, let's imagine that x is in this direction. Let's try to use our intuition. If I'm pushing in that direction, and if I stay in front of a force, I'm getting a push, right? So I'm waiting for P wave.
Yes.
If I stay in the back, I'm waiting for a P wave, but in the different direction. It's a pull. If I stay on the two sides, I'm not waiting for P waves, because these are compressions and rarefactions, but I'm waiting for S. So actually, what we are waiting for is a radiation pattern. That is not in the spherically symmetric problem. There is no pattern there. But now we are waiting for a pattern. Plus, minus, 0, 0, and shear, 0, 0. Let's see. Okay, so now this is the F term, and we have to break it into, using Helmholtz Theorem, a scalar and vector product. Can we find them? Can we find them? Yes, we have to do the procedure suggested for the Helmholtz Theorem. So, for example, let's build the function W. That is the solution of the Poisson equation. Okay, some algebra here. Here we have a direction. It's the integral over the volume, and there it is. It's nice. Okay, if it is a delta, it's a delta. 4 pi is coming from the symmetry, 1 over r, and it's pointing into x1. Given W, now we have to find the two potentials. We have to take the divergence and the curve. These two will be these two potentials. Now some painfully vectorial algebra here, because we have to take spatial derivatives, divergence and the curve, but now we found these two. So F can be broken into these two pieces. If now we have those potentials, we can go back now to the two wave equations. And thanks to Stokes and introducing the direction cosines, does it mean that actually now you're pointing into the source, and you can use some angles, like for example colatitude and longitude, that are telling to you your position with respect to the direction of the force. Are you ready? The solution is this. But it's beautiful, isn't it?
The solution of what is this?
The initial problem, look,
Okay.
let me go back. Wait, too much. Okay, Helmholtz Theorem, okay? Hint for the solution. Can we find, in general, these two potentials? Yes, let's solve the Poisson equation. Take the divergence and the curve, and you got them, okay? Good, let's go to our problem. Let's use Helmholtz, not only for U, but also for F, and after some painfully algebraic passages, we go here and here. Now, can we solve this problem? Maybe yes, if we know this and this. Let's take a specific example for this, and let's give a look to them. The example is this. We're going to look for these two potentials, solving Poisson equation with the divergence minus the curve, and we have the two vector the scalar and vector potential. Let's insert in those two equations and let's solve them. And that's the solution. I'm skipping all the algebra here. There are 2 pages of algebra. This is the solution. Wait a second. Let's forget about x. We don't care. If it is a delta, it will be a delta. If it is a singer, Pavarotti is singing here, it's Pavarotti singing. But, okay, if it is a delta, a delta, a delta. So, it's just for generality. Now, u of I is the solution of, in terms of a vector of a displacement somewhere, okay, u at a given position of t respect to the origin. Our seismograph, okay? The three components of I are related to the Green's function, because the Green's function is a vector whose first index is telling to you the 3 components at the receiver given 3 components at the source. Okay? Okay, so that's the Green's function. How it is made? With these 2 pieces. Wait a second. Because before falling into desperation, we can give a look and maybe we can find some friends here. Yes, we have 2 friends. Which ones? These 2. Because these 2 are exactly the friends that we're waiting for. It's a P wave, it's an S wave. Good, so if we wait, the time necessary for a P wave to reach us, there it is. If it is a delta, you have a delta. Good. It's arriving at the P time, and this is arriving at the S time. They are spherical waves, because they decay as 1 over distance. Good. For pi is here. For pi is here. Well, square and square, it's coming from the algebra, but it's related to the 1 over the square of the velocity in the simplest case. Good. What are the news here? These 2 pieces here, because these 2 are radiation patterns. With directional cosines, they are telling us, according to your position with respect to f, what you're going to feel. And you will see how they are simple in a specific case, in the next page. So, actually, what we were waiting for, due to our intuition, these are 2 pieces with the radiation pattern that we were looking for. Let me make just an anticipation. You will see that the radiation pattern will be a bilobe of P, and for S wave, it will be a bilobe in the opposite direction. It's in the next page. So, those 2 are what we were waiting for. Good. We should be happy. Thanks to Helmholtz, Lamé, Green, and Stokes, we have it. But wait a second. What about the yellow piece? Oh, we were not waiting for. What is that? Ah, that's funny. And now you see 2 nicknames. Because you see that the blue or green box is called far filter. And you should say, okay, it's the normal. 1 over distance. These are 2 beautiful spherical waves. Right? Yeah. Look at the yellow box. The nickname that is there, it's called near filter. You should ask, why near? Why near? Because this term here that we were not waiting for is falling with the cube of a distance. So after some distance, this will be much smaller than the other one. That's a tricky part. Because actually, it's not easy to say when you are in the near field and when you are in the far field. But for sure, after some distance, this will win and this will disappear because it's falling in a very fast way. It's a mixture of P and S waves because it's arriving after the P and with the S. You will see it has a radiation pattern, and you will see in the next two slides how it's made. That will be a new friend that you're going to use also with Alessandra Borghi. Okay, let's give a look to them. The green or blue box is called far field. Wait a second, do not mix far field condition with far source condition. Because today we're living with a point source acting in one direction. So it's a point. So remember, far source is the nickname that we have given when we were using the representation theorem to the point source approximation. We are so far from the finite source that we can consider it as a point. Far source, near source, okay? This condition here is far field and near field. And it is defined also for a point source. Far field.
I'm sorry. When we first started the lecture, you said something about near field displacements. Is it the same with this near field? Okay.
Now you will see, I hope. Let's first consider what we were waiting for. So we invited friends for dinner. There we are. The far field term is made by or a P or an S wave. Good. It's decaying as 1 over R. Good. It's a spherical wave. The source time function at the source will arrive at the receiver. Good. It's homogeneous and blah, blah, blah. So no dispersion. It has a radiation pattern. Because that game with direction cosines, actually, if you write it out, it will go. The first term for P will go like that, because it's a cosine. So if this is the 0 direction along the force, it will be maximum here, it will be minus here. So it's like a beam, okay? A double beam. And we were waiting. If the force is pointing to me, okay, I'm going to get a P wave. If it is on that direction, I will get a pull, push and pull. Nothing on the sides. Because actually, let's be plot. Okay? Let's imagine to see it from the top. It will be maximum. You see here, I hope. It will be maximum in this direction. And minus in this direction. Okay? It's like a cosine. What about the S term? Okay, it's complementary. 0 here, no shear, maximum shear in the other direction. Good. It's going with the sign. And now we can imagine a synthetic seismograph. So let's imagine that we have a force here pointing. Okay, if I'm staying at a given distance, I have to wait for the P wave to reach me. And if I stay exactly in front, my seismogram will be, after given time, if there is a delta there, I will get a delta here, right? And the amplitude of the delta will be maxima here and there, with opposite signs, of course. Okay? And what about the amplitude? Well, if I move more far from that, it will decay as 1 over R. If I stay on the sides, I will get a maximum S in this direction or in that direction. Okay? And if I move far, it will decay as 1 over r. But if I stay here exactly in front, I will get an OS. If I stay there exactly at 90 degrees, I will get an OP. So, compared to the wave physics course, we know these two, P wave, S wave, but now we have a radiation pattern. That is very simple, cosine and sine. Okay? Is it okay up to now? No, it's not, because I'm sorry, but you have not attended the wave physics course, I guess. Or do you have additional questions? Are you lost with 1 and 2?
For one, no.
Okay. 2, it's the wave physics course. I'm sorry for that. Because we spent some hours on P waves and S waves. I cannot repeat the course for you. Maybe if you go to the yeah, it's there. We demonstrated this in one of the first lectures, if you remember, in general terms, and we found them at half of the course. What is new today is this. So these are news for you. You know, all the previous slides have been using a lot of wave physics. For example, in wave physics, we discussed this equation here. That's the elastodynamic equation. And we spent a couple of hours there, so I cannot repeat. But it's there. If you go to the wave physics page, are you getting my message? Just an addition. Voglio che non essere artefatti o mai?
Io non sono documentata.
Okay, speriamo bene. Now, if you go here, so for ICTP people, you know that you have the Moodle website for theoretical seismology, okay? Now, if you go back here, okay. If you go to the wave physics, it's here. At the end of the story, after the definition of stress and strain, nice, right? Thank you. You will see that the equation of elasticity are starting here, and these are the definition of elastic constants. Okay, here we go. That's the equation of elastic motion. And later, there it is. This is exactly what we have been using today. Homogeneous medium, and there it is. This is exactly the equation that we have been using today. From your faces, it seems that you do not recognize it. Now, if you do remember, we have been using the Helmholtz Theorem for this equation here, and we have found P waves and S waves. But if you do remember, I told you, let's forget about F. If you want to study the motion of this table, okay, let's balance gravity. Let's start from the equilibrium. Let's wipe out F. Today, we rediscovered F not as gravity, but as a body force. Why? Because we've used the representation theorem. Okay, let's be logic. Actually, after these two slides, okay, P wave equation, S wave equation. So what we added today are the inhomogeneous terms related to F. Okay? So I guess that you are missing this part. It's there. We spent one course on it. So, but if you want, everything is here. Okay? Okay, so I told you, we have been inviting some friends. Okay, let's have dinner with them. But we have a problem. There is someone else knocking at the door.
Yes.
What is this?
So
No one is invited, but it's fair. Now, the near field term nowadays is very well studied, but I will tell you in the next slide why. If you rewrite it, the term, using the Heaviside function, you can break, let me show it to you again. Too much. Okay, this term here, that is this integral here, and you see that there is 1 over the distance q in front, can be rewritten in a simpler fashion like that. Again, I'm not going to ask you the algebra, but definitely I will ask you the physical message that we have here. Now, if you write out these Heaviside functions that are step functions, you know, Heaviside function is 0, because a given time, then a step, okay? H stands for Heaviside function. Okay, that near field term can be rewritten with the sum of these two. What is this? Well, the first, that is falling off with 1 over the cube of the distance here, is a ramp and then something that is left there. The other term that is falling off with the square of the distance is a ramp after a p wave, an additional ramp after the s wave, and then this. And you have to sum them. These are falling down with different decay. But the message to take home is that that near field term that will disappear sooner or later is leaving a static displacement. So near to the application of a force, and you leave it, remember, when you apply a force, you're not doing something like that. You are applying and you leave it there. Around the application point, you will have a permanent dislocation because that ramp is not going to 0. But if you move far from the application point, it will disappear because it's falling off very rapidly. That's why it's called near field. You should ask, how much is near?
how much is it?
I don't know. I don't know. A sort of a solution or answer to your question is related to the study of Henkel functions, cylindrical waves. But I'm too lazy. So, as a first order answer to your question is, okay, when Kr is much larger than 1. What is K?
It's like that.
And we can write it in many fashions. For example, so when the distance is much larger than wavelength, the near field is no more there.
Independent of direction.
Independent by the direction, it disappears. But if you move at distances that are comparable with wavelength, it's there with the radiation pattern. It's very elusive.
So this near field, the first test, but I'm confused. Is it equal to the sum of this? Or
Yes.
that's multiplying the sum of
Sorry, a plus is missing here, if you want. It's the sum.
the first expression is not part of this two lines.
It's multiplying
Okay.
all of this.
Oh, okay.
I'm sorry, I was trying to squeeze the expression and put the picture. So plus plus, yeah, plus is nice, would be nice there, okay? And the curly bracket is taking all together.
Okay.
Now you could say, thank you Helmholtz, thank you Green, thank you Stokes, but we don't believe you. We believe for P wave and S wave as a spherical wave with the radiation pattern. We invited that. But what is this? let me jump to one of the last slides. Do you want to see it? There it is. If you remember, during the first lecture of this course, what's happening there? Some Green's function?
Maybe.
Some noise is there. Okay. If you remember, during the first lecture, that was the introduction, I was showing to you some pictures from the Toku event. One of the pictures, let me go back, because I have a better one. I think that's the best one. Do you see something there? These are displacements coming from GPS, Alessandra Borghi.
Yesterday also we talked about the talk.
Okay, now let's give a look to this one. Oh, that's fine. It's starting with some P waves, S waves, surface wave, whatever. It's there, then going to 0. Now let's give a look to this. Oh! That's it. It's there. How much is near? Well, okay. You see, this one does not contain it. But this, the earthquake was here, they have it. And the pen is not going to 0. But after some distance, okay, it vanished. Please do remember that if you take the derivative of this, 0, constant, in velocity you cannot see it. But with displacement, so if you have a GPS there, before and after the event, it will not go back to the origin. So it's a permanent static displacement. Okay? So now you can proudly say, wow, it's the near field. Or you can say, no, it's the co-seismic displacement. Karim is going to use this term, for example. Alessandro is going to use this word. And actually, it's this. You see that the arrows are very large there, but then they disappear. So that's why the near field term is important. And there you go. Wait a second. It's not enough. Because if you want to attend Alessandra Borghi's course with the proper solution, theoretical solution, that is not enough. Can you tell me why? What have we discussed up to now? The Green's function. That we invoked during the representation theorem, right? And what is the Green's function? It's the solution of a lasso-dynamic problem when everything is a delta in the inhomogeneous term. Delta in time, good, we did it. In space, yes, we did it. In direction, now we did it. Is that enough for earthquakes? No, because actually we do not can relax here. Because yes, we invoked the Green's function, but actually at the end of the story of the representation theorem, we discovered that the beautiful representative force for an earthquake, for a shear dislocation on a fault, treated as a point, is not a force. It's a couple and another one. It's a double couple. I'm sorry for you, and also for me, but that's not the final formula for today, because actually what we should write is now the solution of a double couple. I'm sorry for that. So we can use the representation theorem in its simplest fashion, so a point source And you do remember that the equivalent body force of the shear dislocation is a couple with a seismic moment m0 multiplied by the moment tensor. So what we have to do now, sorry for that, is to take the Green's function, that is a solution to a force, apply an arm, consider a couple, consider another one, and consider another one. What does it mean? Algebra. Okay? But I hope that the logic is clear. Now we found the g, now we have to take a spatial derivative, to take another g, to take another spatial derivative, and sum them, because we need a double couple. Is that clear, the logic? You remember representation theorem? We discussed it 2 lectures ago, okay?
Yeah.
The end of the representation theorem is this writing here, okay? The convolution of a moment tensor, PQ, remember, is weighting the Green's function n. What does it mean? But now we have to make this algebraic development of this expression here, and you know what? Bad news. But we're going to skip the algebra. But let's use intuition. What are you waiting for? Who are going to invite now? It's your dinner. You're the host. Who are going to invite? You don't want to eat? Yes, let's eat.
I want to eat, but I don't want to have more guests.
Okay. Sorry if I'm joking about that. We solved this problem. And we found radiation patterns, right? Simple ones. Sines and cosines for P and S, right? Now we have to take this with an arm here and compute a spatial derivative. You have to solve this, take an arm and this, and to sum them. What does it mean? That we are waiting for P waves and S waves. You aren't going to invite them, you have to, but with more complicated radiation patterns. This is what we are waiting for. We are waiting for P and S waves falling with 1 over R with more complicated radiation patterns. And that's it. Remember to leave the door open, because some new friends will enter, because we will have a near field also here. Actually, we have 2 new friends. Let's give a look to the blue box. These are the friends that we invited. Thank you. And one is a P wave, the other is an S wave. Good. 4 pi, density, and the cube of the velocity. Good. These are all friends. 1 over x. Spherical. Good. But wait a second. Now our friends are a little bit different, because the spatial derivative that is here with the change of variable is taking here a time derivative. Yeah. They are more lively friends, because now they are more rapid.
Okay,
That's funny.
It's faster than
Not faster, because the velocity is here, and here it's bad, it's given. But we are a little bit more happy. Good. What is written here and here is just a nickname for the radiation patterns. And we will see them in the next slide. They are just a little bit more complicated than sines and cosines. Actually, they will be sines and cosines of twice the angle. But you have to leave the door open, because someone else is entering. And we have the yellow box. Okay, well, we met it. That's the previous dinner, okay? But there are also 2 additional terms here. They are called intermediate and near. But the far is 1 over square, 1 over 4th power. So they decay very fast. And sooner or later, they vanish. So that's the end of the story. After all the tour that we started with the representation theorem, please do remember what we did. We took a shear dislocation on a fault. We tried to heal it, taking integrals, and to look for representative body forces. And we found them, a distribution of body forces replacing the slip of the fault. Then we said, and how we found that? Defining the Green's function. Remember, the Green's function was there. Actually, it's here. This is the end of the story for the representation theorem when the source is a point. Far source condition. Okay? Good. Today we discovered how G is made. And then, now, in this slide, we're taking a partial derivative for a couple and taking another couple and summing them. And that's the solution. And now we have far field, far source. Now we are using both the conditions. We are so far from the source that it is a point, and we are so far from the point that we're taking just the friends that you invited. And this is the piece that we're going to use from today on. So we will be living, except some slides, we will be living in a far source, far field condition. And we will look for focal mechanisms. Okay? But you can stay with the far source condition and consider the near field terms. And those two expressions are the ones that are at the base of the theory when you study static displacements with a GPS. That's the simplest model that you can use to model those arrows that you have seen for Toku, for example. Okay? So the take-home message for today is, okay, we developed representation theory. We have used the Green's function definition. We considered the far source condition, and we found this expression here. Green's function, the partial derivative of the Green's function, means to make Green's function. When you take a partial derivative, you create a couple with the arm in the other direction. Okay? Okay, we need two of them, double couple. They can be described by a moment tensor, symmetric, homogeneous is the medium that you are considering. The moment tensor is symmetric with a null trace and with one of the eigenvalues 0. It's a double couple. Good. Today we developed the Green's function expression, the slide before this one. We are applying the representation theorem in the far source condition with some Penny algebra that we skipped. We can get this. And when we decide to stay in the far source, far field condition, this is what is left. A P wave, an S wave, spherical waves with radiation patterns, and the temporal information that is traveling is the derivative. One fact that we are going to use in the next lectures, do you remember when we described the fault with something like that? Okay. Zero, slip, 0. Okay? This is the duration of a slip. 0, slip, 0. Okay? The time derivative of this will be the box. this is the piece of information that is traveling, because it's the time derivative of the slip function. And this is what we're going to use in the next lectures. By the way, this is called rise time. Thank you for your dinner. We have a friend here. So in the time domain, what is going to be propagated is a boxcar with the duration of the slip. Is that enough? No. But we will see. Oh my God. There you go. Radiation patterns. Okay. What are these angles here? These are nothing else than direction cosines that we have to use to specify our position. I'm sorry for you, this is called theoretical seismology.
Yes.
That's it.
That's mine.
Okay. Let's imagine that we have the source here. Okay? And we are a poor receiver here. How to describe it? Well, we could use, for example, Cartesian orthogonal system. It will be terrible because we are going to lose the radiation pattern symmetry in terms of angles. What we can use is a sort of a spherical reference system centered into the source. This is R. And now, you know, that's the R direction. What about the two angles? Well, one could be the colatitude. The other could be the longitude. Oh, that's terrible. Okay, let's imagine it's falling here. Okay, a sort of a longitude. It's nothing else than specifying our position with respect to the source. With those two angles, there you have your beautiful radiation pattern for the far field condition. It's more complicated than the single force. Of course, we have four forces. Don't worry, because there will be a picture from now on of this. And that picture is what we're going to use on Friday to find out focal mechanisms. So the beautiful beach ball representation that we are used to use to describe earthquakes when they are points. So the beautiful game between black and white will come out from this. So, thank you for the dinner. We will leave you some presents, and the presents will be focal mechanisms. But please do remember that if you stay near to the source, you have to take care about these two, and they have their specific radiation pattern. And please do remember that our behavior at the dinner will not depend on our time function, but our derivative of a time function. Question. Why we have only this time of information here? So, oh, by the way, you can imagine other functions here. If you want, the simplest one is a step. I am so fast in slipping that it's a step. Too fast. But if you take the derivative of a heaviside function, it's a delta. But in a more realistic fashion, it will take some time to slip due to the slip velocity. Okay, that time is called rise time. You can imagine something more, okay, complicated. It will be maybe less regular than a boxcar, but that's it. Question. Why do we have just this time information? Because a few lectures ago, we found that the rupture starts somewhere, propagates, and the slip field can be heterogeneous. Where that time information has gone? Maybe you close the door too fast. We don't have this information here because we're using a point source. It's a point. Rupture time is lost. Please open the door. And let's run out. No. Sorry for joking about this, but remember that when we use a point source approximation, we are squeezing all the information in a point. So we are forgetting about rupture time. Could be long, could be much longer than this. So when I'm doing this, I'm moving at the same time all the fault. Don't worry, they will knock at your door, okay? And rupture time will have 20. We will see that. By the way, let's relax a little bit. Okay, this is the piece of information that you have to take home if you want to be polite with Alessandra. Because that's the piece of information that is left there when you consider the static displacement after a double couple. I know it's a mess. And this stays for near field, intermediate field for P, intermediate field for S. It has to be written like that. You see it's decaying faster than the far field. It has a radiation pattern. And this picture here is there to show to you what is the reference system that we're going to use, not today I guess, but on Friday. So we have a fault here, a slip on the fault. Do you remember our simple model that we developed at the end of the last lecture? Okay, and you see we have a receiver here, we have a radial component. It will contain P waves, right? Because P waves are longitudinal. So we are pushing in this direction. While shear waves will be perpendicular. So they will act into these two directions. Which ones? Colatitude and longitude. So this is the reference system that we are going to use. And if you want to give a look to the static near field double couple, okay, there it is. Why it is infinite here? Because it has infinite period. It will never come back again. It's not a transient. Okay, so we are. This is a transient. 0. Seismogram, 0. Oof. End of the story. This is 0. Some wiggles here that actually, if you scale them, they're like this. Look at 240. So these wiggles here are like this. But wait a second, we are 2 meters and 2.4 meters up now. We will never come back again. So it's not a transient. That's why it's called static. And that's why it can be considered a piece of information at infinite period. It's so long the period, but it's infinite. And it will depend on M0. Where are we? So if you want, that's the slide to save, to work with Alessandra Borghi. For the part of the residual static displacement. You can call it co-seismic. So we have radiation, a wave passage. This is a wave passage, but is leaving there a message that is forever. Okay? Now some pictures to end this painful lecture. That's why in terminology you can call it co-seismic deformation. And in the recent earthquakes, you have many pictures that can be taken using GPS or INSAR. So you use a satellite, you take a picture before, a picture after, you have permanent deformation, like that. So these fringes here are the trace left on the ground that will never go back again. Remember that this information here is spread around the fault, then it disappears. It's near field. Okay? And you see that these lobes here are dependent upon the mechanism of the fault. That's the radiation pattern. So you can call co-seismic deformation. You can work with the theory that we developed today, maybe to make it direct modeling, to compare with data, and to make an inversion. And the nice animation that I've shown to you very rapidly during the first introductory lecture is here again. Because if you imagine a GPS, then you have a before event pre-seismic charging, and then you have Pong elastic deformation, and the GPS will never go back to the equilibrium because it will be moving near the fault. It's near field. Charging, so it's between events. Okay, co-seismic, and then the relaxation due to viscosity is called post-seismic. And if you want to see in reality, there it is. So those arrows there are called, as you can see here, co-seismic displacement, horizontal and vertical. You see how fast they decay here. They're zero there. End of the story. There you can record just far field, and you have a beautiful wave functions that we have seen. They are transients. Okay? So, co and post-seismic, and the final classical old picture, this is coming from the first edition of Aki and Richards. This is what we're going to use from now for 5 minutes and the next lecture. Because now we have all the tools to predict something. Thanks to the presentation theorem, we found the double couple. Thanks to the Green's function, we found the solution. Well, complicated dinner, we have new friends, but now we're going to use the old friends, so we can use a piece of information in the far source, far field condition. The source is a point, it's a double couple, and we are using just the far field term. And we can predict something. Okay, now let's imagine, and this is what we're going to do to find the beach balls. We can take the first part, the top left cartoon is showing a fault with a slip, okay? It's the one that we have studied. Now we can imagine to take a, so if you remember, I was using a sort of a x1 direction, z as a normal of the fault, and a slip, okay? Now we can create a reference system around this, in the center of the fault, maybe represented as a point. And we can imagine to give a look at different angles. Let's imagine to give a look from the side. What we are left here is with theta. And the radiation pattern for P waves, it will be like that. It has 4 lobes. It's due to the sines and cosine that you have seen before. Sorry, let me go back. These two. You see? So now let's take phi as 0, and let's give a look to the fault from this side. From your point of view, that's the fault, okay? Theta is describing this position. Okay? You see, it's simple. It's sine of 2 theta. That's for P, and that's for S. This is the piece of information that we have to use now. And what we're left with is this beautiful picture. So we have sine of 2 theta, 4 lobes, and wait a second, because we will have a maximum here, maximum here, maximum here, but plus, minus. So a push and a pull, a push and a pull, right? Now let's imagine to take this radiator, to place it in the Earth, and let's predict the different polarities that we can record in the world. And let's make some phone calls. What have you got there? Plus, thank you. Minus, thank you. Nothing, because here you will have nothing. And we can imagine to take those polarities, to trace them back, and to give a look to the fault. And to look at the direction of strike, dip, and rake. And this is the building of focal mechanisms. What about S waves? It's complementary. One is sine of 2 theta, the other one is the cosine of 2 theta. So you see, where you have the maximum of P, you have 0 of S, and vice versa. And the information that you are getting here is not pull or push. And remember that your seismograph will be, for a push, it will be up, for a pull, it will be down. This is a little bit different because it's a shear. So it's not up and down. Remember, S waves. Pure shear. And these are the lobes. But if you give a look at a sphere that is surrounding the source, you will have this 4 lobes pattern. And here you have this 4 lobes pattern, but wait a second, because here you have planes that are along these directions where you have no motion. Here you don't have planes, but just poles where you have no S motion. Remember that S waves are perpendicular, transverse. So we have these 2 visions. And just using this vision here, we can make a model, imagine polarities around the world, compare them with the recordings, up or down. Okay, we take back the information, and according to the distribution of plus and minus here, we can rebuild strike, dip, and rake. This is what we're going to do on the next lecture. And that's why the next lecture is called, it's called focal mechanism. And after a brief introduction on Friday, we will use this piece of information. That's the starting slide for the next lecture. All the friends that you invited home are there. We will forget about the new friends. We have just limited seats, so we cannot take whoever. And what we're going to use is to take the information of a P wave, spherical, an S wave, spherical, with radiation patterns, longitudinal, transverse, with some time information that is the derivative. It's called rise time. Question, just to conclude for today, and we will be like in Japan, very short. Tell me in just a few seconds, which part of a wave field will be larger on average? Forgetting about the radiation pattern. Radiation pattern now you know, according to the position related to the source, we can feel more P or more S, according to the angles. Let's take an average. Who will be the largest friend at dinner? Oh, well, the fastest is easy, P. P is faster. So, P waves will sit first at the table. But which one will take a larger place? look at this. On average, S waves will be larger because S wave is less. So they are slower, but at the denominator, this will make them larger. That's why S waves usually are larger. So please, when you prepare the table for the dinner, take a larger seat for S waves, okay? Okay, you see, this is the expression that I told you is one of the most powerful coming from this course. Moment tensor, there is M0 in MPQ, remember? So that's why M0 is also here. So the amplitude will be proportional to the moment. Time, decay, radiation pattern, normalization that contains the cube of the velocity. Remember that here we are using far source, far field condition. Not exactly Japanese. Remember also one other thing. The Green's function that we found today, and it was really painful, is for a homogeneous, infinite, elastic medium. So, I will not, there are some hidden slides. I closed it. There are some hidden slides. Because remember, they are not, I don't think, I was hiding them. Remember that every time that you enter into a more realistic medium, the Green's function will change. Are you going to put a free surface? Okay, Rayleigh waves, reflections, PP, PS, SP, you remember, PSV, SH, right, and Rayleigh waves. Are you going to put a layer, low velocity layer? You can have direct, reflected, refracted, and head waves and lag waves. Are you going to put a stack of layers? So you have everything. Remember that the Green's function is the solution of the single force applied in one direction in a medium. So if I clap my hands here in another room, in a beautiful conference room, or in a concert room, the sound will be different with the same clap. So we solve just the simplest problem. Homogeneous, isotropic, infinite. The Earth is not like that. So please do remember that it's not a game over.
Okay.
It will be for us,
That's what it is.
because I was hiding the slides. But they are beautiful, I guess. Look.
Yes.
But they are hidden, okay? So we will start again with the slide, far field, far source. But remember that sooner or later, we will need to take care about the rupture time. And now is squeezed in a point. Okay.